Hey everyone, today we are going to be talking about the least squares method for a linear regression algorithm, and I want to start by showing this graph, and I'm going to start by telling why linear regression is somehow interesting. From my perspective, it's one of the most interesting algorithms in the machine learning because of its simplicity, and because of its simplicity, it's a little bit different from others. It's like it's like water in the world of other chemicals. It's the most common one, but it has some unique features. Speaking of the linear regression, in most cases we use the cost function called mean absolute error that, if we graph, looks like that. So you should notice that it has one global minimum. And I think throughout the course you have all thought that about the heart of the machine learning, that there is a certain algorithm, a certain function that we need to fit with data, a certain cost function that we fit with data, we get a certain value, and we have the cost function for almost any algorithm, for almost every algorithm. And because I think everybody is aware of what the derivative is, and everybody has thought, from my perspective, that why can't we just take the derivative of the cost function itself and calculate the parameters mathematically without iterating, without using gradient descent. And the thing is that most of the derivatives of ordinary cost functions are transcendental. What it exactly means? It means that we would get something like that. It's a transcendental equation, the most common one: x plus cosinus x equals 1. It looks easy and it seems easy on the first glance. Of course, derivatives of cost functions of log loss, for example, they look more complicated, but the heart of them is represented by this equation. We cannot solve it mathematically. We cannot use anything to get something like x equals something something something. And that is why gradient descent is introduced, other algorithms are introduced. They are just solving the transcendental equation this way. They use Newton's method, for example. We'll talk about it a little bit later. We use gradient descent to solve them, but because of the simplicity of the linear regression, we can use a certain method called least squares method that lets us jump that's the closed function graph, to jump from this point A, from the random point of its function, straight to the global absolute minimum, so to the best fit value of parameters. And as I have told you about the derivatives and the stuff with the equations, we just take the error and we just take the derivative of it, say that it's 0, and then solve the equation. So let's do that iteratively with me, but not iteratively, just step by step. First, let's introduce our cost function. Today we're gonna talk about it as some kind of a vectorized thing. So where y and x and w. Today we're not talking about it as theta, but still as just a vector of parameters. Those are actual vectors, and I'm not saying that 1 divided by n, because as you understand, when we took the derivative of it, we would still get rid of it. So I got rid of it on the first step. So we have this thing. We say y minus x powered by multiplied by parameters squared. It would give us a value. Let's work a little bit with this loss function in the vectorized way without taking the derivative. And this slide is so-called beginning from the cost function itself. So we just say that from the calculus that this square thing equals the transpose thing multiplied by this thing. So it's a basic formula from the calculus. And then we just open the brackets by saying that this thing y minus xy transposed equals y transposed minus xy, and this thing is transposed. Just open the brackets, and then we understand that firstly we need to understand that xy transposed equals y transposed x transposed. The order by which they go matters, but still and by understanding that, you can understand that y transposed x transposed y transposed x minus x transposed y just equals v transposed x transposed and y. So we just say it's minus 2 of them. I'm saying v transposed x transposed y instead of y transposed x y, just for the sake of the derivative itself, because we're going to take a derivative from it, so obviously it looks better, because in the derivatives we mostly work with the transposed vector thing. So next we take the derivative of it. We have this thing, and let's use the chain rule. Let's take the derivative by h of all of the things that we have here. The derivative with the perspective of v of our parameters from y transposed y is 0. We don't care about that. The derivative of this thing is just minus 2 negative 2 y x transposed y, because we work with the transposed matrices when talking about the derivative, just like x with an ordinary derivative. So it's like negative 2x transposed y, and then we use the derivative formula for this thing, because we have y transposed and just y. So we say that this thing we consider x transposed multiplied by x as just a, let's say vt a v. So, and the formula says that the derivative of it equals a plus a transposed v. So, and notice that x transposed and x, and when it's transposed is the same. It's a constant. It's some kind of a value. So we just see that equals 2x transposed xy. So we have this thing, and now we say that it equals to 0. And the easiest thing that we can do, we can just solve it, say that 2, we get rid of it, take this thing to the 0, and then say that y equals x transposed x powered by negative 1, so it's in the denominator, multiplied by x transposed and y. So that's the least squares method, and with this parameters we can just, this w parameters, we can just go from the point A straight to the point B. So by finding the w, we can just do that. So that's everything I think for today, and we would also work on this least squares method in a little bit different way when we talk about the locally weighted linear regression, which we would be talking about in the next video. So thanks for watching.